Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I would like to show you and discuss a little bit about a certain circuit that is essentially a timer for a bathroom fan. We will start from one circuit that has been reverse engineered by one of my friends, by one of the followers of the other electronics channel that I have. And we will move over to another circuit that I designed that, in my opinion, is better due to a number of reasons. So the idea is that there are certain fans that you are supposed to install in your bathroom, and they work in the sense that you can turn them on. They typically turn on once with the lights, but when you turn off the lights, the fan is supposed to still work for a couple more minutes or maybe even longer. In order to extract whatever odor you have in your bathroom, even after you're gone from the bathroom. And there seems to be a certain model that is very popular on the market. One of the followers of my other channel, which is of my other electronics channel, which is in my language, has had such a fan. He had it broken, and because he wanted to see how and if he could fix that fan, he made him reverse engineered, and he basically sent the schematic to me. And yeah, I thought it was one of the stupidest schematics that I could have possibly expected to receive. But anyway, I'm gonna talk a little bit about this and a little bit about how I would see an improvement to this delay circuit or timer circuit. I don't know how you might call this one, that leaves a fan turned on even after you turn off the lights in your bathroom. First of all, please allow me to speak a few words about the sponsor of this video, which is PCBWay. When you want to build circuits and you want to have them built comfortably, then manufacturing them at home could prove to be more difficult. So you could potentially employ the services of a company like PCBWay, a leading PCB manufacturer with many capabilities to help you build even your most difficult projects. You can easily get an instant quote for PCB manufacturing from the website's front page, upload the Gerber files, and have your PCB created in just 24 hours. If you need more to get your project finished, they also offer PCB assembly services with manufacturer direct pricing, so you can have your PCBs delivered with components soldered on. This way you don't have to do the tedious work yourself. Or if you do want to do the tedious work of soldering SEMEDE components, you can order just the SEMEDE stencils, and then you can solder the components yourself. Just finish your design in your favorite design software, upload all the necessary files to PCBWay, and you'll be contacted by one of their professional representatives after they manually review your project, offering you one-on-one customer service to make sure that your circuits get fabricated just the way you want. If you're building a circuit for a device that will need a case in the end, they can also help you with this matter as well, offering you 3D printing or injection molding services to have your custom-made plastic case, or perhaps CNC machining services to help you with a custom metal case. All you need to do is go to PCBWay.com, the link is in the description. Thank you very much, PCBWay, for sponsoring this video. Now let's get started with the two circuits that I want to show you. So like I said, this circuit has been reverse engineered by this friend of mine, by this person that follows my channels, and I just couldn't believe. Like, don't get me wrong, it's after all a personal opinion. I'm not a professional electronics engineer, but I found it stupid that some people actually used digital integrated circuits to create a timer circuit to just turn on and off a fan. It seemed overkill to me, and it just doesn't make any sense. I'm not gonna bother explaining the entire circuit because I don't see it valuable. What I will say is that they used an IC that has 4 NAND gates. I hope I remember correctly, or maybe it's OR gates, NOR gates. Anyway, and 2 of these are basically used as inverters because both of their inputs are connected together. Anyway, like, I just laughed, but apparently this model is manufactured in large quantities and it's sold in large quantities, especially in some countries. This friend of mine happens to be in UK, well, in England to be more precise. So apparently there, this is a popular design. I could only think of 2 potential situations in which a company might want to design such a circuit. One, the situation in which that particular person that has designed the circuit knows very little about analogic circuits. He has learned more about digital circuits because, you know, nowadays most people are a big fan of digital circuits, especially microcontrollers and such. So I'm guessing when this guy was given the task to design such a circuit, he just couldn't design a fully analogic one because he just didn't knew how to do it. So it was easy for him to think in terms of some logic gates and some extra components around. That is one suspicion. The other potential explanation might be that this particular company has had a lot of these digital ICs in stock and they just wanted to get rid of them, and they were like, okay, now we need to build some bathroom fan timing circuits. Let's see if we can just use those digital circuits so that we can just get rid of them because we just have too many. Like, other than these 2 situations, I can't think of a reason why someone would want to use an IC with 4 different gates and a whole bunch of other components around. That, on top of the fact that it's strange, it also consumes a certain standby current constantly, no matter what. Okay, because as we can see, the upper wire, the upper line, represents the phase, or what you call live in certain countries. The lower wire represents the null, or what you might call neutral, and we have this switch here, which is basically the same switch that you have in your bathroom to turn on and off the lights. But this switch here basically turns on and off a current through a particular portion of the circuit, not through the entire circuit. Of course, it couldn't, because the fan needs to remain turned on even after you open the switch, right? So you have the phase and the null, which is constantly connected to the circuit, and it a current constantly flows through here, through this 27K resistor that limits the current through a Zener diode that basically offers a stable voltage across her. We also need a rectifier diode so that we don't pass both both polarities of the alternative current that, you know, is powering the entire circuit. We also need a small filtering capacitor. Anyway, this portion of the circuit will always consume current, and this is a problem for, you know, the monthly consumption, which translates into wasted money, and also in the overall lifespan of the device. I mean, if we have a current passing continuously through some components, of course we can expect them to burn sooner rather than later. And if I'm not mistaken, it's exactly this 27K limiting resistor that got burned in the circuit of my friend. Anyway, I have simulated this. You can just calculate, make a simple calculation, but I've actually simulated this in microcap earlier, and in standby this draws about 1.8 watts, therefore 1.8 watts hour, and so on a monthly basis this circuit alone consumes 1.3 kilowatts. Now, even in my country that doesn't mean much, but again, it's more a matter of principle. Why have something consume current constantly, even when he's not doing anything, when we could have a better circuit, a better design, you know, that actually does the job, and when turned off, he actually shuts himself down. And this is what I've done. This is what, you know, I've taken as a bit of a challenge, and this is what I've created, both in the computer and in microcap as a simulation. And later we will go to the workbench, and I will show you a bit how this works, so you know that I'm not just showing you something theoretical, I'm actually showing you something that is tested. So the idea is very simple, right? We have a triac that we need to basically turn on and off. Nothing unusual. We have a triac here in the original schematic as well. I chose to use a diac as well to basically turn on this triac a lot faster. They didn't use such a thing in their design. Truth be told, they couldn't have used, because this IC has a maximum of 15 volts power supply rating. I'm guessing that this IC is actually powered by 12 volts here. A diac needs about 30-ish volts to turn on, so obviously they couldn't have used the diac here. Anyhow, and basically I want to have a switch that once switched on, it will stay on for a certain amount of time. Of course, I will need to use a capacitor to charge up to a certain voltage, and then a resistor to discharge him, but make sure that he doesn't discharges, you know, as fast as possible, but actually discharge in a relatively long time. So this is in essence what they did in their original design. They have a 470 microfarad capacitor in parallel with a potentiometer that I don't know exactly what value he has, but we also have a 188K resistor here. For me, it's well, at least in this experiment that I've made, because again, what I'm showing you here is more like a circuit. In principle, you can just change the values here more or less as you see fit. I have used a 100 microfarad capacitor and a 2.2 megohm resistor, fixed resistor, because I don't care about changing the timing for my particular experiment. Of course, by increasing the value of the capacitor and or the resistor, we will have a longer time of the whole circuit turning on our motor, our fan, and by decreasing these values, of course, we will have a shorter time. Just like in their design, I needed also a rectifier diode, current limiting resistor, in my case 33K and 2 watts, it needs to be at least 2 watts, and a Zener diode to basically provide a certain voltage that is, you know, workable for high value capacitors. It's easy to find a 100 microfarad or even more capacitor that can last, that can resist up to 63 volts. The higher the voltage, then the more expensive these capacitors become, and the bigger they are, and yeah, we would have problems. So I just chose a 39 volt Zener diode because I'm not using any integrated circuit, so I can use pretty much any voltage that I want, really. Now, unlike in their design, where they use the 47 microfarad filtering capacitor that is separate from the 470 microfarad timing capacitor, for me, this capacitor is the only one that is used for both filtering and for timing. Actually, I don't really need filtering for anything. This is just a timing capacitor. I don't need I do need another capacitor, but for a different thing, and this can be a lot smaller. This is just a timing capacitor. I don't care about filtering anything, and I'm using this particular voltage across this capacitor to turn on and off Darlington pair of NPN transistors, model MPSA44. These are 400 volts and 300 milliamp small power transistors that are cheap. Everything here really is cheap, and this is another advantage of the circuit. You know, you can get a 1 microfarad capacitor that can go up to 400 volts, and I will explain why we need here this in the moment, for basically 5 cents if you buy 100 pieces at once. This 100 microfarad capacitor is 8 cents, and one transistor is also 5 cents a piece if we buy 100 pieces of each. So all in all, this whole circuit is €1, maybe even less. You know, I haven't calculated the resistors and the diodes because those are even cheaper, I think. Anyway, the essence is that we are using this Darlington pair as a switch to later switch the triac on and off. Okay, and this Darlington pair is switched on first and foremost when we close this switch here, which is the light switch. And when this light switch is opened, this capacitor will keep this Darlington pair turned on for longer until he discharges, you know, completely. And this once this Darlington pair opens, current flowing from the 220 volt line through this D1 rectifier diode and R2 15 kilo ohm minimum 3 watts resistor goes towards the diac and then later the triac, and yeah, this is turned on. We still need an extra limiting resistor here, 3.9K and about half a watt. You can put two resistors in parallel of 6.8K each in order not to buy a special half a watt resistor. Anyway, and that's pretty much it. And we need this 1 microfarad capacitor because, well, these transistors will not be able to be functioning for both polarities of the input voltage, right? Because we have a rectifier voltage here, so only on the positive side of the alternative current, these transistors will work, but we will want to keep the triac open for the negative side as well. So this is why I chose to put a 1 microfarad here in the collector. This basically acts like a bucket of energy, because this capacitor is charged from D1 and R2, and as long as the circuit is turned off and remains off, this capacitor will basically remain charged indefinitely without actually consuming current from the input, right? And when we turn on this whole circuit during the negative voltages, this capacitor will provide a positive voltage to the Darlington pair switch, which will then power the diac and the triac, right, from this 1 microfarad capacitor slash bucket. And really, this is all that there is. Okay, I don't have an actual fan, so I just put two 33 kilo ohm resistors in series as a load, and I'm also attaching an oscilloscope across them so that I can see. I can take a look at the waveform and see when the whole circuit gets turned on and off, just for, you know, demonstrative purposes. Normally here you would connect the AC motor, the AC fan, or whatever, or even a light bulb, whatever it is that you want to be controlling through this circuit. Overall, this circuit would occupy less space, so basically you would be able to build this on a smaller PCB. I do believe it's actually cheaper than another circuit that actually needs an integrated circuit, and like, yeah. And last but not least, maybe the main advantage is that when this Darlington pair is turned off, because this switch is open, there is absolutely no current flowing whatsoever through here, which means that we actually have zero consumption from the power, and therefore zero money to spend when, you know, we're not actually using the fan. So there's not much rocket science going on in here. Let me take you to the workbench and demonstrate this practically. I just need a moment to get there. Alright, so what do we have here? Let me turn on my oscilloscope. Sadly, I'm filming during the day and I have quite a bit of sunlight, so yeah, please excuse you know, the reflections. I think now it's worse. No. Let me see if I can do something somewhat better. So now you should be able to see a yellow line here, okay? And I'm going to be having a clock here, a chronometer. Now, before I start, let me remind you that you should not do any of these things unless you are really comfortable working with you know, high voltage and dangerous circuits in general. Okay, so if you're not comfortable, don't do anything, don't build such a thing, and don't start using such a circuit. Okay, what else do we have? We have here a counter that is able to measure voltage, current, and calculate active power and well, energy, but you can ignore this energy from some previous experiments. and I have a safety switch here. And also the switch that is in the schematic, which is basically the light switch that also turns on the fan, for me it's this particular crocodile cable. Okay, so I will power everything on, and making sure that I don't touch anything dangerous, I'm going to basically turn on the circuit. Okay, and we see this because we have a sine wave here, and I'm going to release this and start the chronometer. So now it's the equivalent of me switching off the light, but as we can see, the circuit still gives power to whatever else, such as a fan. And we have a full waveform for about a minute. And then we will start having half a waveform, and then things will turn off completely. So the circuit is not 100% perfect, but for a simple AC motor that, you know, spins some blades and blows some wind into your bathroom or out of your bathroom, you know, it's not bad. So now we see that the waveform is kind of deforming a bit, and we are close to 1 minute. Now at close to 1 minute, we have only half a waveform. So now the fan would still blow, but with, I don't know, half a power or so. And then at about 1 minute 40, I believe, this would just turn off completely. And what's most importantly is the fact that we have, I mean, we already have 0 watts, because since I'm not actually powering a motor, you know, the current here is really low. Okay, 1 minute 30 something. I was talking with you and I forgot to stop at that point, but anyway, about 1 minute 30. As a reminder, this time can be easily increased by having a larger timing capacitor, larger timing resistor. Yeah. And as we can see, so now the circuit still receives power, because this master switch is turned on. Okay, so I still have power here. I still need to be careful about not touching anything, but 0 watts of consumption, absolutely 0 watts. Okay, and I'm gonna turn this on one more time, make one more demonstration. Okay, click, and we see that now the power has gone up to 1.7 watts or so. Now that I am taking this away, I only have some power through my load, which is a 66 kilo ohm resistor, right? It's still decreasing, and again, at the end, as you saw earlier, we have absolutely 0 power wasted, which, needless to say, it is an advantage. So that's pretty much it. I don't mean to keep you waiting any longer. This will turn off one more time in a few seconds. So all in all, this is how you are supposed to design such a timing circuit. I mean, it really makes no sense using more complicated circuitry, right? I'm gonna switch back to the circuit so you can see him one more time and draw him on a piece of paper or make a print screen. This is what I would do if I would need to, you know, design a timing circuit for anything really. So I hope you found this useful. Thank you very much for watching this video. Don't forget to like and subscribe if you would like to see more videos in the past. Sorry, in the future, not in the past, because we're moving forward. I am definitely constantly working and studying new things, so once in a while I come here on this channel and show you something that I consider to be interesting so you can benefit from him. Thanks a lot for watching, and I will see you next time. Bye bye.